Hi everyone, welcome back to our ScaledGD seminar. So today it is our great pleasure to have Professor Yuejie Chi from CMU to give us a talk. So Yuejie received her PhD from Princeton, and before that she received her bachelor from Tsinghua, the same as me. And I know Yuejie for her many great work on algorithm and the circle foundations of signal processing, machine learning, such as matrix factorization problem, base retrieval problems. I know many of her work. And recently she works on reinforcement learning, but today she will talk some her recent work on accelerating ill-conditioned low-rank estimation scaled gradient descent. So with that, let's welcome the speaker.
Okay. All right. Thank you very much for inviting me. It's very nice to be back here. This is actually my third time visiting Michigan. I already had a lot of fun interacting with the single processing group here. So it's nice to be back. So today I'm going to talk about some recent work on accelerating ill-conditioned low-rank matrix and tensor estimation problems via a new algorithm we proposed called scaled gradient descent. And this is a sequence of papers that I've been working on this sort of algorithmic approach for the last 3 years, actually a little bit more than 3 years. And this is joint work with my student Tian, who has already graduated, and current student Harry, and incoming student Xingyu, and also Kongma's team at Chicago. All right, so I don't really need an introduction, a motivation for why I'm interested in low-rank structures for this audience, but we're getting a lot of new data coming from interesting imaging and sensing modalities. And in order to sort of processing this sort of new increasing amount of data, we really need new tools in computation that are sort of scalable in terms of its both the memory use and computational time use. And particularly in a lot of the application I'm interested in, you can think of the data arranged in kind of an array structure, where if you look at the spectrum of these matrices or tensors, they tend to have only a small number of significant eigenvalues or has a very fast decaying property. So in other words, this data has, generally speaking, a low rank structure. And that sort of is often the case because really the interesting information you are interested in are kind of latent structures in this high dimensional data that only encodes a small number of salient or interesting quantities. And this sort of range across imaging application like radar imaging, hyperspectral imaging, to recommendation systems, biomedical and bioinformatics applications, and so on and so forth. So many of the problems can be solved through the sort of canonical formulation of a low-rank matrix sensing problem, where roughly speaking, imagine you are interested in some sort of low-rank matrix M has a dimension of N1 by N2, where the rank R is typically much smaller than the ambient dimension of this matrix. Instead of directly observing this matrix, but rather you're taking indirect measurements of this low-rank matrix using some sensing device. And here I'm thinking about maybe sensing devices can be well modeled through some sort of linear map A, resulting into a number of measurements Y. And in particularly, we're interested in this so-called sample stopped regime, where the number of measurements or the sensing budget M is typically much smaller than the ambient dimension of the matrix M. So you can't just use like a standard or naive least square estimator to estimate such matrices. But maybe your sensing budget is fairly larger than the underlying degrees of freedom of the low rank matrix if you count, so say, the number of unknowns and the number of parameters that is necessary to parameterize this low rank matrix. So we really need to have algorithm that can harness this underlying low rank structure in order to solve this problem properly. And one of the sort of major advances in the maybe around last decade-ish is a sort of convex relaxation approach that try to solve the problem by doing convex relaxation using nuclear non-minimization. And to think about the problem, basically, imagine you want to solve this kind of rank minimization problem where you seek the matrix with the smallest rank that started produce this kind of observation that measurements that is consistent with your observation. However, the rank constraint is NP hard, and you can't really solve this. So what you want to do is to do this convex relaxation by minimizing the so-called nuclear norm of this matrix, which is known to be kind of the tightest convex relaxation you have for this kind of rank constraint. And there has been significant developments in the last decade trying to understand the performance of such convex relaxation algorithms, where people have been demonstrating there's very appealing statistical performance guarantees for this kind of convex relaxation paradigm for a number of different measurement operators and so on. However, the downside with this approach is it often scales very poorly because you are operating in this sort of ambient matrix space. You still need to store and process these matrices of large dimension, and this sort of nuclear non-regularization typically give you semi-definite programs that scales polynomially in terms of complexity with respect to the dimension of the matrices. So it's not a good approach for dealing with high dimensional data. With that in mind, the people have sort of resulted to this kind of low complexity approach based on matrix factorization. And the idea being, if you have some knowledge about the underlying rank of the matrix, you can try to solve this kind of rank constraint least squares estimation problem instead. And if you know the rank, you can immediately write out the factorization of this matrix Z into a product of two skinny tall matrices X and Y, where the memory complexity only scales now with respect to the degrees of freedom of this problem rather than the ambient dimension. And you can instead write this rank constraint optimization problem now into a unconstrained problem over the factor matrices X and Y, right? So it's fairly straightforward. And intuitively, this is going to be more scalable. But on the other end, the problem is also non-convex because we can no longer sort of specify these factors uniquely. So you'll have many global optimum to this globally optimal solution to this problem. And generally, it could be hard to talk about global convergence guarantees. But nonetheless, there has been quite an interesting line of research along this perspective, trying to, it turned out that we can say something much more positive about the performance of this kind of algorithm by leveraging statistical insights into the analysis of the optimization algorithms. So the main insight being, if you look at analysis coming from traditional or conventional optimization theory, so that typically worst case analysis that sort of give you guarantees for the worst instance of the problems. While in reality, often the data we are collecting from sensing modalities are not that adversarial, and they often have some maybe randomness and nice statistical properties associated with them. And if you leverage the statistical models in the analysis of the algorithm, you can actually show the in average case, the trajectories of the algorithm can be much more benign and give you much better performance, even for very simple algorithms. And one of the typical simple algorithm people would think about is like a gradient descent type of algorithm, where you simply update the parameters along the descent directions of the gradients. And so we've seen a lot of success along these lines of thinking for a variety of different problems where this kind of low rank matrix factorization problem actually plays a very important role underneath a lot of these recent successes. And if you look at what we know, and now revisit this sort of low rank matrix sensing problem in terms of what we know about this, you can see that typically what people are doing is trying to directly minimize this objective, but not quite. The literature actually often look at the so-called gradient descent, but with a balancing regularization, which tries to sort of balance the size of the left and the right factors. And once you do this, that's help you to sort of create a nice local basin of attraction. In the sense, you can basically follow a two-step update approach where the first step basically tries to construct some nice initialization, often using the so-called spectral method. In this talk, I will not be focusing on the spectral method, but basically we'll try to, ask you to trust me that such an initialization can indeed be found if you have good sensing operators. And once you have a good initialization, you can then basically update the factors along the descent directions of this regularized loss functions in a typical gradient descent fashion. And we know this result from this paper by Tu et al. Back in 2016, where they essentially showed for such low rank matrix sensing problems, if you had the underlying low rank matrix to be exactly rank R and has a condition number, which is basically the ratio, the largest non-zero singular value and the smallest non-zero singular value, then if you use vanilla gradient descent, the algorithm will converge linearly with a number of iterations that scales on the order of kappa log 1 over epsilon. So it's a linear rate of convergence with a pre-constant that scales linearly with a condition number, as long as the sample complexity is fairly larger than the degrees of freedom up to some polynomial factors of the rank and the condition number. And there has been a lot of similar results being established for many other low rank problems, such as matrix completion, robust PCA, and so on and so forth. It seems people have generally constructed pretty good understanding of performance of vanilla gradient descent for solving this kind of low rank matrix sensing problems, as long as you have a good initialization. All right. Now, what has been bugging me about this result is the dependency about conditioning number. Because coming from a signal processing perspective, a lot of the older applications I work on, such as super resolution, really are dealing with U condition problem, where the condition number can be very large. And indeed, if you look at this kind of results, for example, you run a matrix completion problem, very standard one. The only thing I'm changing is a condition number of this low rank matrix. And indeed, the algorithm converges linearly. However, the slope of this convergence rate becomes slowed down as you increase the condition number. So this kappa constant in the convergence rate is not an artifact of the analysis, but it indeed happens in practice. And we all know from optimization theory, this is generally true if you're running vanilla GD algorithms for optimizing even strongly convex problems. Right? So the question is, can we actually accelerate this? But before that, let me tell you why I care about this using a toy data example that's kind of useful for me to illustrate my point. If you look at the sort of naive data set that I put on the internet, sort of measures coloring concentration levels at some water junctions. So this is really just a data matrix of size 120 times 180. And we know if you compute the spectrum of this matrix, often for real data, you will observe some kind of power law decay. And this is what we use to motivate why low rank structures are so prevalent in practice. That often, if you just do a kind of low rank approximation, say rank 5, which preserves 88% of the total energy of this matrix, you already get a condition number of 20. And if you want to preserve a little bit more energy by doing only a rank 10 approximation, this gives you a condition number 60. This number may not look that big, but remember the size of this matrix is only on the level 100. So they can, in some cases, become even proportional to the ambient dimension of the matrix, making the convergence extremely slow, right? Okay. So we have to pay attention to the condition number, right? How do we do that? So my goal is actually try to accelerate the convergence to a rate that is not just getting to square root of kappa. I guess some of the audience who are experts in optimization are thinking, well, you can do momentum that give you square root of kappa, but I actually want to be a little bit more ambitious to even completely get rid of it. And then particularly paying attention to gradient type algorithms. There are other type of algorithms, such as, for example, alternating least square type of algorithms, where the convergence rate is independent with the condition number. But the per iteration cost is actually much, much more expensive. Is basically sweeping the condition number under the rug of per iteration cost. And there's also additional benefit with gradient descent, where if you have a distributed scenario, it's very easy to parallel gradient descent type of algorithm. So anyway, so we want to work within this kind of gradient-based algorithms. by trying to accelerate the convergence by getting rid of the condition number. And that brings into sort of the scope of this presentation. I will start by looking at directly this question, trying to design fast algorithms that are insensitive to the condition number, where we only add a minimum overhead to the per-iteration cost. And then I'll sort of try to see if there's other regimes we can also use similar ideas. And one of the regime is, can we actually also look at scenarios where your measurements can be potentially perturbed or corrupted by adversarial outliers? Can you still design this robust variance that are simultaneously oblivious to the existence of outliers and also bad conditioning? Moving forward, I want to look at generalization to tensors. Can we extend similar ideas to tensors? It turns out with tensor problem, conditioning number become even more serious issue, and it turns out this idea can also be used to tensor problems. And finally, I'll talk a little bit about going beyond this regime of doing local optimization with spectral initialization and think about issues related to overparameterization. All right, so let's directly get into the first aspect, which is really sort of the essence of the talk. If this is a 2 slides you want to listen to, it will be the next 2 slides. And then you can go to your computer and work on other things. So this is the algorithm we come up with that we call scaled gradient descent. And what we really mean is, instead of using the vanilla gradient, we are going to use this sort of scaled gradient, which is also people in the literature also call preconditioning and so on. So there are 2 things we are doing here. First of all, it turns out we don't need to have the balancing regularization anymore. The algorithm kind of automatically adapts to it. We are going to do the same initialization as before, but locally, instead of doing the original gradient updates, we're going to do this preconditioning. And the way the preconditioning works is, if you take a left factor, you're going to precondition it using information from the right factor. And it based on your current iterate. Okay, so it's time varying. So you do this Y transpose Y. And Y is a tall matrix. So Y transpose Y is a tiny R by R matrix. So if you just do this inversion, it adds little computation. And often you can actually combine the computation with a gradient to make it even cheaper. And similarly, you do the same thing for the right factor, but this time you get information from the left factor. So it's kind of this, symmetric view of how you update the 2 factors. If you work with positive semi-definite case, you just have the 1 equation where you just use X instead, right? So it's very simple algorithm. And eta is a learning rate. Okay, so if you just look at what the algorithm is, it's a preconditioned gradient method without doing any balancing regularization. Okay, question? Okay.
So if you know the rank, what if you don't know the rank?
That's the overparameterization part. You have to hold to the end of the talk. Yeah, I'll visit that. Yeah.
So so if you had 3 factors, what would be like? Do you think there's like a similar?
Yeah, if you vectorize everything, this preconditioning goes to the front. In the paper, we wrote it down.
Okay.
Yeah.
So if you like X, Y, Z.
Yeah, if you vectorize these things into vectors, because these are matrices, right? If you vectorize everything, this actually goes to the front, and then there's a Kronecker product with some identity matrix before you multiply this. Yeah, so it's actually connected to doing some kind of quasi-Newton method, but you are not computing the exact Hessian because that will be too complicated and expensive. What we are doing is, if you think about the problem without sensing operator, just the factorization model, this preconditional design comes from looking at a block diagonal approximation of the Hessian. Yeah, the details is also in the paper. Yeah, we have more discussions in the paper about some interpretations. Yeah.
That your comment answered my question.
Okay.
Oh, sure. So my question is like, why is the the comparison between this scaled gradient descent and the vanilla gradient descent? Why is here a balancing regularization? Is like some intuition, probably like something implicit.
Yeah, I can tell you direct. So this is a landscape from this vanilla loss, and you already see this is very different from the one with balancing, because with balancing you fold this area around, right, to create a quadratic ball-like shape. And what happens along this edge, so these are all global solutions, right? So if these two factors has very different scales, one has a very large scale and the other has a very small scale, then you have to use very small step size to offset that unbalancedness, right? And that is basically what happens. But if you think about what this factors are doing, it offsets that scaling issue intuitively, right? So you will actually, in the previous vanilla GD algorithm, the learning rate has to be scaled with respect to the largest singular values, right? But here we can basically just use constants because of this, yeah. Yeah, I'll tell you a little bit more. I have some intuition slides too, but you guys are already ahead of me. But yeah, so this is just a advertising slide to show, yeah, in the previous matrix completion problem, now if I run ScaledGD, I have the same convergence curve. Now this is not counting the runtime, right? This is iteration count, but so they all align actually with the scenario where you do vanilla GD, but with perfect conditioning. Right, so we will have a huge computational saving. Again, this is only computational saving, not statistical saving. We'll have a huge computational saving where now the algorithm converts in a condition number independent manner, where with a minimum overhead to basically compute the small preconditioner. Yeah.
So if you do the balanced GD, will you get a similar benefit?
No, so with the balanced GD, this is all this orange curve.
The vanilla GD.
Yeah.
Okay.
So balancing is also not that necessary with vanilla GD, but this helps analysis as well. Yeah.
So to get rid of the balancing is not the key.
Yeah. Yeah, we have a paper analyzed the vanilla GD without balancing, but the kappa will still be there. Yeah, so let's take a closer look about why this helps. One of the key property of ScaledGD that I think is really important is this so-called invariance to invertible transforms. So what happens in these factorized problems is you can't uniquely specify these factors up to some invertible transforms, right? So if I have an iterate specified at xt, yt, that give me this low rank matrix at t, and if I run the algorithm for one iteration, I get to xt plus 1, yt plus 1. I could alternatively parameterize it differently by using some different invertible matrix. It's the same low rank matrix, but if you run vanilla gradient descent on this iterate, it give you a different iterates. It leads you to somewhere else. Well, for this new version of gradient descent, you get to the next iterate that will be covariate with respect to these parameterizations. So in other words, if you think about the trajectory of the algorithm for low rank matrices, you always get the same trajectory on that low rank manifold, no matter what parameterization you are using for these factor matrices. And that is really one of the key properties that makes the algorithm nice. Okay. Of course, in terms of analysis, our goal is not just to show the algorithm actually converges, right? We want to show formally the algorithm indeed can give you accelerated rate of convergence that is independent with the condition number. And to do that, it turns out that we need to go beyond the previous analysis framework. And one of the most important things is to realize you can't use the original distance metric either. You have to come up with this new Lyapunov function that measures the distance to the ground truth. So what people have been doing before is basically you measure the distance of these factor matrices to the ground truth by sort of aligning them properly, right? Look for the invertible transform that sort of give you minimized distance. But here we also have to introduce this scalings. That is, kind of in accordance to the preconditioners in this distance matrix. So the distance matrix is actually not time varying, right? So sigma star here, it comes from the spectrum of the matrix and is fixed. And then once you have the distance metric, you do a careful trajectory-based analysis to look at the progress of the algorithm in an iteration-based fashion. And that gives you the rate we want. Question?
Yeah, so you said this distance is used for measuring convergence. Is that what it's for?
Yeah.
Okay, thank you.
Yeah, so you will have like the distance at t's iteration and t plus 1's iteration and so on and so forth. And you can show contraction of this. All right. This seems to somehow it's not working anymore. Okay. So we have this theorem basically shows if you do this ScaledGD algorithm with spectral initialization, now we can probably accelerate the convergence now within this order log 1 over epsilon. Now you don't see the pre-constant about condition number anymore, as long as the sample complexity is basically at the same level of requirement as the previous work. So basically this gives you a strict improvement over the prior analysis that shows this algorithm can probably accelerate vanilla gradient descent at the same sample complexity. Okay. So we went on to look at this algorithm for a couple of other low rank estimation problems such as robust PCA and matrix completion. And the general message is pretty much the same, that basically under similar sample complexities as required by the vanilla GD algorithm, we can basically accelerate the iteration complexity by probably getting rid of the condition number. Okay. Yeah.
I think the condition number dependence of the sample complexity is like fundamental too. And
oh, very good question. Yeah, for this kind of non-convex problems, we don't know how to get rid of it. So it's an issue with all this non-convex analysis.
and do you see it also in practice, like if you run experiments?
Good question. I think it's less an issue in practice.
So maybe
But yeah.
not as extreme.
Yeah.
So this condition number is the condition number of the latent matrix Z, right?
Yeah.
Because there's also the sensing matrix A, and I would think the convergence rates are.
That's a very good point. It's in the paper also. So indeed, if you have a general sense, because with sensing problem, the condition number that you just described is a constant. It's 1.
Yeah, that's true. It's not.
But you can have a general, because it's quadratic, but you can have a general F under RIP, sorry. So it's not a constant. I was thinking about matrix factorization is 1, but with RIP, it will be a constant.
I see.
Yeah, sorry for
Because you have to
confusing you.
choose your step
Yeah,
size.
yeah.
You need to choose your step size, I assume. Let me word the question more broadly. I was surprised your preconditioner only considered the latent matrix, not the sensing matrix, right?
Yeah, I have a version where I look at this. This general loss function.
Okay.
Okay. Where this is low rank and then you do factorization. Okay. And then you have another condition number coming from this.
Yeah.
So if you do GD for this, the iteration complexity will be kappa F times kappa.
Okay,
And we're getting rid of this.
got it. Thank you.
For this, I suspect you can do momentum to get to square root, but I haven't done it yet. I'm waiting for my student.
Hopefully they're working on it as we speak.
But this is like, yeah, this exactly, you have two condition numbers. Okay, so now we have sort of the basic version of ScaledGD. Let's look at what else exists. Yeah.
Can you explain again what's the intuition of get rid of condition number with that?
Yeah. The intuition, if you think about the two factors, right? What happens is if you have different eigens, you have different components in your spectrum, right? Some has larger eigenvalues, some has slower eigenvalues. And if you want to make all these components to converge at the same time, you have to always listen to the slowest person in the team. Right, and then you have to use a small step size, and that slows things down. And that's also true for general optimization, right? For gradient descent. By doing this scaling, you kind of have, make sure they are sort of on the similar pace. And then you.
Why doing this make sure they're on the similar pace? That's what I.
Yeah.
How that like relates to the eigenvalue.
Yeah. So well, if you just, even for one component, right, you have this issue as well, I think. Well, not with one component, two. Yeah, you have to have at least two components.
I think
Yeah.
if A is the identity operator or the vec operator, I think your preconditioner is the solution that would give you would give you the exact update to X. It would solve the problem for a given Y, right? So in that sense, it's like a Newton's method. No, it doesn't, not even.
Because I have I have step size here.
Well,
So it's an interpolation of what you were describing.
One and A is like identity, it's still not.
It is,
Oh, it
yeah.
is,
That's why I say it's an interpolation between what you described and the previous one.
So that's my intuition.
Yeah.
I don't know that it would give you the right thing if A were the identity, and for random Gaussian, if A transpose A is kind of like an identity, I think, so.
Yeah. Yeah, I have to come up with a better interpretation for you.
I also need to think.
But also for the distance, right? This is also why we need to scale it here, because this is a diagonal thing, right? That so you have to scale different components to kind of balance things off. Yeah. All right. Okay, so now let me move to some of the extensions. One, the immediate extension we work on is adding some robustness considerations to the problem. Because if you take take this low rank matrix sensing problem, but you may have some maybe sensor failures or malicious attack, so that some of your measurements can be adversarially corrupted. And if that's the case, your measurement model will be additionally perturbed by the addition of an outlier term S, which I'm taking as some sparse vector that but can take some arbitrary values in the non-zero entries of it. Right, so I'm only constraining the fraction of the outlier as some small number alpha. And obviously, we cannot use the least squares loss anymore. But in the literature, people resort to the so-called least absolute deviation loss, which basically look at the sum of the absolute values of the residual vector. So you can do similar two-step approach for optimizing this non-smooth loss function. With a caveat now, instead of doing gradient updates, you need to result with this kind of sub-gradient iterations. And you have to carefully pick the learning rate to some kind of maybe Polyak learning rate or geometrically decaying learning rate. So this approach turns out to suffer from similar slowdowns if you have yield conditionings. And by now, you know what I will do is basically adding these preconditioners, right? And magically, basically just working the same way as earlier, where the main takeaway is basically if you take our approach and compare with some of this prior analysis, we can show a speed up in terms of convergence rate by the factor of the condition number, right? So now we have this kind of nice non-smooth subgradient method that is robust to both yield conditioning and adversarial corruptions to the problem. Okay. Yeah.
So in this plot, I see like the different paths for like the different condition numbers, but like where does the adversarial noise come into this plot?
Oh, it's not in this plot. This is for some maybe fixed level of corruption.
Okay.
I think the paper has some plots that varies the level of corruption. Yeah.
I thought subgradient was like order square root of K number of iterations instead of order 1 over square root of K, not over 1 over K, right? So
What is K? Kappa?
number of iterations. I think in terms of number of iterations, you think of.
Okay.
But
Yeah, this is again for the special problem, low rank sensing, for example, where you assume you have some RIP property and then you adversely crop some fraction, and people have some stronger analysis, which again go beyond just like a vanilla subgradient method analysis.
Yeah, compared to the vanilla gradients, well, the solution you find, well, maybe ultimately you care about X multiply Y transpose. I mean, will the X and Y transpose recovered by vanilla and scaled version be different? Assuming
They will actually give you the same solution if you give them say like enough number of iterations to run, but just ScaledGD converges faster. Yeah, I probably have some example at the end to demonstrate that.
I use a diminishing step size for the subsection, for example.
Oh, yes. So for this, you have to do some kind of geometric decay step size because otherwise you will overfit if you use constant. Yeah. Okay, so it's nice that we can do all this with matrices. What can we do with tensors, right? Increasingly, we see a lot of applications that people are collecting tensor data, which are so this higher dimensional objects that are nice to capture multi-way, multi-dimensional interactions across different imaging modalities. So naturally, we want to do similar things that we've done with matrices to tensors and think about how we can solve such low-rank tensor recovery problems. And it turns out that with tensor, there's many different ways that you can define low rank based on different tensor decompositions. And one of the tensor decomposition we look at is this so-called Tucker decomposition that has this complicated definitions. But pictorially, you can imagine what this is trying to do is you want to, if you take a high dimensional, let's say 3-dimensional tensor, you want to reduce this into 3 tall skinny matrices UVW with a call small size tensor S, where the S has this so-called multi-rank, I think, or multilinear rank, I say R1, R2, R3. So this now you have 3 different rank parameters, and this thing has a much smaller dimension. While this UVW are like those low matrix factors that we've seen earlier. Okay, so this is just like an intuitive way to think about this. Okay, and the problem we're interested in again is this kind of low rank tensor recovery problem. If you have maybe some sort of measurements of the tensor, how can we recover this low rank tensor from the measurements? And surprisingly, tensor problems are much more challenging than matrix problems. Just quoting some evidence from the literature, we've seen that if you do convex relaxation for matrices, we have this nice nuclear norm that is computable using semi-definite program. It turns out that if you do the same for tensors, the nuclear norm of a tensor turned out to be NP hard to compute. So even you can do convex relaxation, that doesn't give you computable procedures. In addition, there is also this conjecture about computational barriers with tensor recovery that people have connected to this kind of tensor recovery problems to some hardness conjecture in theoretical computer science, where they claim you can only get polynomial time algorithms when your sample size is above the order of n to the 3 to the 2th order. And this is surprising because if you count the degrees of freedom in prescribing the low rank structure of the tensor, it only scales linearly with n, while this computational barrier has a superlinear dependency with n. Okay. And when we started working on this problem, it's also a surprise that since there's little existing results for the Tucker case, there is actually no probably efficient first order algorithm for low rank tensor completion under the Tucker decomposition. There's some previous works that try to analyze like regularized, like when you do balancing, regularized gradient descent problems for sensing problems, but not for completion problems. So all this kind of motivates us to look at this problem. And since we now know this scaling trick, we want to look at, can we actually do the same kind of scaled gradients for tensors? Now, because we are working with more factors, it's not clear where we can start. But intuitively, this is a way to imagine what could happen. to construct the algorithm. Let's say if you do an unfolding of the tensor by just basic unfold like different fibers of the tensor into a matrix. And this gives you actually a low rank matrix, which has a factorization where the left matrix is this factor matrix U, and the right factor just combines all the information from the other factor than the call tensor. So let me call this U graph, okay? And this give me enough evidence to mimic what I did with a matrix case. I will just treat this as a matrix problem for updating the left factor U. So the way I'm going to try to update my left factor is to do this gradient update, right? Multiply this preconditioner, that pulling information from this U graph, okay? And you can do this for UVW, right? These are the matrices. The last thing you need to do is figure out how to update the call tensor. And this has a slightly different form that you have this thing, okay? If you put all the scale gradient update together, this is basically the algorithm we have. And again, the key property is you get the invariance to parameterization. So in this tensor problem, you also have this ambiguity in parameterizing the tensor factors up to some invertible transforms. And this update is kind of also motivated to balance out this parameterization ambiguity. And then you get this kind of scale gradient algorithm. Kind of follows similar spirit, right, as the previous one for the matrix case. And we do the analysis and we can show, if you look at the completion problem, again, the message is you can achieve linear convergence at a rate that is independent with a condition number, as long as the sample size is above this n to the 3 to the over 2 order after some other factors about rank, condition number, and this so-called incoherence parameter and so on. So if you ignore the other thing, this is roughly near optimal, aligned with the conjecture people have, and this gives us sort of the first probable linear convergence result for this kind of low Tucker rank tensor completion problem. All right, so if you look at numerically, you kind of observe similar phenomenon that this ScaledGD algorithms give you just nice convergence that is which has a rate that independent with a condition number. And it turned out if you observe a little bit closer, this condition dependency with the condition number for vanilla GD is actually even worse for tensor problems. In fact, for this tensor problems, the convergence rate depends on the condition number quadratically instead of linearly, but we have a constant rate. So if you do this scaling trick, the computational benefit you get out with tensor problem, I believe generally higher order problems is more evident. Basically, larger benefit can be pulled out by working with higher dimensional objects. Okay, question with this tensor? Yeah.
I have a question. So the main theorem for this tensor setting, can we go back to like 2 pages before? Yeah, so it's like under Bernoulli's sampling, if I remember correctly, for the matrix setting, it's like the Gaussian sampling. So what's the difference? Do you have any intuition?
Yeah, we have we actually have both results. So the Gaussian thing that I showed in the previous is just for simplicity to benchmark with the 2AR result. That one we can also do completion under Bernoulli sampling. Similarly, with this tensor one, we can also do Gaussian sampling with a sensing operator. But that was also actually done in this prior work by Becca, where they analyzed gradient descent. Here I'm just highlighting another result for completion.
Okay, so it's not like a big deal.
No, you can do it for both. Yeah,
Yes.
you get a similar sample complexity. Yeah, this is the main factor. This main factor is always there.
Just curious, will that number R, in fact, the computation complexity of calculating preconditioners?
Where is
The-
the sample
the top.
size?
No,
The kappa?
right.
It's not in the computation. That's
Yeah,
the-
because in a computation, you just look at iteration, but for each iteration, you need to calculate that precondition,
Yeah.
right? Will that?
I don't think it matters because if even you just compute the precondition in the most naive way is cubic in rank.
Uh-huh.
So Oh, so that depends on rank. It doesn't
Right,
depend on kappa. Yeah.
Okay.
All right, cool. All right. Let's see. So we actually, my student also look at this for tensor, robust PCA. And it turns out you can do similar things as long as the corruption level is not too high. But one thing I want to highlight for this is we've tried this for real data, and this is some material science data, like a microscopy data set. We want to use this kind of ScaledGD or RPCA to do like foreground, background separation. And it turns out it's not very easy to use, because often when we use this algorithm for real data, we don't know how to tune the hyperparameters, right? You have learning rates, and if you do RPCA, you also have to have like a learning rate schedule for thresholding the outliers and so on. So if you do some kind of baseline approach, this doesn't give you any kind of reasonable result. And my student Harry is really good with deep learning, and he did this kind of trick where he do some kind of unrolling interpretation of the algorithm, and coming up with a way to use self-supervised learning to automatically tune this hyperparameter that give you much better results. So I feel this is kind of interesting thing to show there is actually benefit to maybe bring in some of the tricks in deep learning in this kind of optimization-based approach, so you can sort of achieve the best of both worlds in some sense. Yeah. All right. So with I think I still have how much time do I have?
15.
Okay, cool. So I'm going to maybe just spend the next remaining time to talk about one piece of unpublished work. So we're a continuation on this theme of looking at scale gradient descent, kind of revisiting Chin's question at the beginning, is what if you don't know the rank, right? By thinking about overparameterization. So far we have been assuming we know the exact rank of the matrix. If we do not know the rank, the immediate thing, the natural thing is to think about, like in this overparameterized regime, maybe you have some upper bound on the true rank, say R prime, and then you can try to do this ScaledGD update in this overparameterized setting. And that could have an issue. The issue is because in the design of the preconditioner, we're doing this inversion here. And if you have overparameterization, this X transpose X can become close to being rank deficient. And then this inversion can become unstable. And more importantly, the analysis also break down. So we want to fix this. And in fact, I think Sarah has a paper on this as well. But I'm calling this related to adding a sort of regular parameter lambda into this regularization, kind of like a Tikhonov way of modifying the preconditioning so that this is always invertible. Okay, so this is just a simple update for the positive semi-definite case. You can do similar things for the asymmetric case. And we can actually show, so this is still not published. We are sort of putting the final touch on it, that basically, if you do small initialization, so if you use a small random Gaussian initialization, you can guarantee the algorithm converge still almost independent, in a number of iterations that is almost independent with the condition number. So in the convergence is kind of this two-phase convergence where the second term is what you see earlier once you enter the local regime. But in the first phase, we have a little bit of log dependency on the condition number still. And this is actually, if you compare this, a similar analysis that is being done for the vanilla GD algorithm, essentially, we basically reproduce similar messages, but now we have this computationally, the number iteration is almost independent with the condition number. Okay, in fact, our analysis also allows us to get exact convergence guarantees when you have random initialization with correct rank specification. Yeah.
So here lambda is fixed throughout the iterations.
Yes, for simplicity, yes, we have a version that is fixed. Yeah, the one I'm specifying here. Yeah. Yeah, so this is just picture that try to show some of the dynamic. I'm not sure whether you guys can see it at the end of the room, but roughly speaking, now this is iteration up to 400, and this blue dashed curve is basically how fast ScaledGD is picking up the signal components. Okay, and if you look at say up to 2000 iterations, ScaledGD is already up here. So it's already pick up the signal component very, very fast. Well, you see GD just barely starts to pick up the signal components. And if you do 4000 iterations, then kind of both algorithm converges. Yeah.
So I'm a little bit curious. Can you go back to your previous slide?
This one?
No, the previous,
Yeah.
the theorem statement.
Okay.
Yeah, so here, as you get closer to the true solution, in your algorithm, or maybe like if you could show the algorithm itself with lambda, yes, here. If X transpose X gets closer to singularity, then the dominating term is going to be lambda times identity.
Mhm.
So it turns into gradient descent essentially,
Mm,
right?
okay.
And then if lambda doesn't go to 0, then I believe the convergence rate should be similar to gradient descent. And that depends on the condition number. So my question is, what would happen if you hit singularity?
It doesn't matter much. Like, for example, I have to double check the analysis, but if you look at what happens empirically, it doesn't really make much of a difference at the end in the final stage.
Oh, okay.
That they actually behave very similar to the original ScaledGD methods.
So by the time
Oh.
you get non-singularity, you're already pretty close
Yeah.
to.
So for vanilla gradient descent, the reconstruction error. Oh, never mind. Okay, I got the two dashed lines confused. I
Yeah,
thought it
these are
started-
bad figures. I apologize.
Sorry,
Yeah,
I thought
I
it
try
started
to
with
illustrate
100.
too many things. Yeah, yeah, but it's just trying to yeah. Yeah. Anyway, so I want to just conclude. Yeah.
So lambda is choosing on the order of a minimal singular value.
Yeah.
How do you choose that in practice?
Yeah.
We have some discussion in the paper how to polish those, but that's that's a there's a data-driven way to do it. My students know how to do it. I don't know yet. but yeah, but this is cleaner in terms of presentation for the analysis. Yeah.
When you multiply the algorithm, you like implicitly like adding some implicit regularization to the objective function.
Yeah, you can almost say that. I think there's a lot of literature that think of the problem in that way, that when you do over-parameterize, right, you have many globally optimal solutions, but not all the global solutions are low rank. So the algorithms is actually have like an implicit regularization that promotes low rank solutions. So that's one way to think of it. I'm more coming from the perspective single person and think of this as a rank misspecification. Yeah. Yeah. So I want to conclude with one toy numerical example on this issue that I think is still unsolved. Is related to rank specification, right? How do you determine this hyperparameter rank? Is the problem really a yield condition problem, or it's really an over-parameterization problem? So again, if you take this toy data set I showed earlier, when you have this power law decay, now if you try to run these different variants of the algorithm for say rank equals 5, you can see that indeed vanilla GD converges very slowly, but eventually you will reach the same error flow with ScaledGD, or this kind of this regularized one. And this regularized version and the vanilla ScaledGD behave pretty much similarly for this problem. However, if you try to take a larger rank, say rank equals 20, and this is where the singular value becomes really, really small. And that starts to cause issue for the original ScaledGD algorithm, that you probably can think of this as a truly over-parameterized case in some sense. And adding in this regularization seems to help. So I think it's an interesting problem to think about where you want to set the cutoff, right? Where you want to select a rank for such problems, and possibly in a maybe data-driven manner. That's something we don't know.
So for that plot, is the lambda the min, like the 20th eigenvalue here?
Yeah, something like that. Yeah. Okay, so just to conclude, I've been talking about this kind of low rank estimation problems through this non-convex landscape analysis, and trying to strike a balance between the computational perspective by trying to get a sort of near dimension free iteration complexity, and also the statistical perspective where we want to have nice sample complexity result that does not scale with respect to the ambient dimension of the low rank matrices. Also adding into the consideration of robustness, where we want the algorithm to be robust to the existence of both adversarial outliers and EU conditioning. And what has been key in this line of analysis and algorithm development is the identification and exploitation of nice geometric properties of this highly non-convex landscape, and trying to analyze actually the iterates, the trajectory of the algorithm, rather than just stay at the level of a black box optimization. And it turns out that some simple variance of gradient descent actually leads to very nice, robust, and accelerated convergence for these problems that go beyond just vanilla GD. My slogan is preconditioning helps. This helps to increase the computational efficiency of vanilla gradient methods, even for some very challenging non-convex problems. We've also been thinking about how to actually use the idea of preconditioning for other signal estimation problems. And one of the other problem we look at is actually a super resolution or spike deconvolution problem, where you could also have different sources that have maybe strong sources versus weak sources, and you have actually similarly a conditioning issue there. And it turns out preconditioning also helps for those problems. If you're interested, we have some papers, and I'll conclude. Thank you so much for your attention. I'll be happy to answer any other questions you have.
Thanks, Yuejie, for a great talk. Any questions for the speaker?
On slide 42, you talked about the theory and practice gap, and I have a question related to that gap. So in the pictures you show cameras and MRI scanners and things like that, but the theory I think was all for Bernoulli sensing matrices and Gauss and matrix factorization. So have you tried this for any real world, or more, let's just say sensors that don't necessarily satisfy REP conditions and other things? Do you think that?
So this is a real data one, and we already see.
But it's just factorization, right? There's no sensing. Right? There's about the sensing, right? Do you think it would work for? I mean, maybe you won't have performance guarantees.
Spectral initialization won't work. The vanilla version with if you have bad like non-RIP sensing operators, I don't think it will work. It's actually quite sensitive. For matrix computation also, if you have non-uniform sampling patterns, there are people look at maybe modifications, but that's actually one of the major issues.
Let me know.
Yeah, if I circling back to my comment in our morning discussion, I mentioned that I think a lot of the benign landscape results only hold for a limited number of cases. Unfortunately, even so for average analysis, we know on average is good, but in application, we still end up in some of the corner cases where it's not as benign. Yeah.
Thank you. Terrific talk. Really interesting.
Thank you. Yeah, I think the theory provides some guidance on algorithm design, but we have, as theoreticians, we need to acknowledge the limitation of our work. Yeah.
I have a technical question related to overparameterization again. Do you think that log kappa you have is because towards the end, the algorithm becomes more like gradient descent, and less.
Oh, I had, yeah, it's possible. I have to check the net. So I'm adding a lot of details on the slides. It's not the original version of the theorem because the basically the alpha, right, will enter into the final bound. And the alpha translates into some of the iteration complexities. So that could be true. I have to just look at the original version, you know. I'll send you a copy when the paper is ready. Yeah, thanks.
At the beginning, you have mentioned that you can also solve the problem in XY and with regularization. And
You mean the balancing regularization?
Yeah.
Oh, okay.
so with this result, well, your result in XY in your solution will have like similar properties as their regularization.
So we don't need that. Yeah, it's automatically, well, it's balanced in the actually we don't need balancing at all. Since if you how many animations? Yeah. Here, right? If you start with something highly unbalanced, it will still be unbalanced, but it doesn't matter because you can when you look at the distances, this will be factored in like by this, right? So we actually balancing is not necessary in these problems for it to work. It's an analysis artifact that you want to have a strongly convex like thing. If you don't do balancing, you don't get locally strongly convex landscape. Yeah.
So just a intuitive question, like, do you think, so like, let's say we're doing like 2-layer neural network and then like X and Y are like the weights. Do you think preconditioning would like the one that you have would help in that case for that kind of optimization through like the nonlinear activation? Like say like X sigma Y.
Yeah, maybe. Yeah, if you have a homogeneous ReLU is easier if you have nonlinear activation because you don't have rotation ambiguity. You only have permutation ambiguity. So you get a diagonal preconditioner that probably will work.
But for neural network, it could be very like you don't have low rank.
I guess maybe if we have like a low hidden neuron and then like just try this maybe.
You could have something like a superposition of neurons where the weights of the neurons have a like a spectral decay, like a larger, smaller one. So you get condition numbers there as well. Yeah. In a lot of this problem, you just have a different notion of the condition number.
And I guess, you know, if you have a lot of neurons, like there's works that says they're low rank.
Yeah.
And then maybe the scale lambda trick can.
It's actually might be related to this cyclic convolution problem. Yeah.
Even if the underlying solution is low rank, the parameters are not lower, so that matrix inversion could be very costly. Right.
You mean for the over-parameterized
Yes,
setting,
over,
right?
like,
Yeah,
overall.
yeah, definitely. Yeah. So that's why I think if you have a single processing problem, you don't want to do that over-parameterization. You want to pick the right rank and then do the smaller problem. Yeah.
I have a small question. You can explain the intuition why we add lambda.
Yeah, I know that too. Right? Yeah. If you think about maybe solving least square problems, right? Where if you have U conditioning or rank deficiency, you add Tikhonov like regularization, right?
Yeah.
That give you lambda I. Yeah,
Yes.
that's just an intuition.
And for my thinking, it can be defined like as a new inversion. For example, suppose we can do as a BD, we only invert the no zero part. But for zero, we should keep it. Then we don't need the lambda.
Where do you want to do SVD?
Suppose we don't have lambda, so sometimes if we do inversion, maybe sometimes the inversion
Yeah.
don't exist.
Yeah,
We can define
empirically.
new inversion.
Oh,
suppose
so
it's
pseudo
SVD.
inverse, right?
Like define new inversion. suppose we SVD X transpose X, so we only invert the one, is no zero, put zero to keep the zero. So we still can do the inversion. But because I think sometimes in some Newton methods, because sometimes the Newton method is not a global convergence or forget the cubic methods. So sometimes when people do, so sometimes people also add lambda. Sometimes people didn't add lambda, just still do inversion. But some not true inversion as we know, right?
But if you keep it zero, then you won't make progress in specific direction. So it's like saying your step size is zero towards that direction. You need that lambda to be non-zero. Right, so
Yeah, if you have like exact over parameterization, again, if you think about intuitively what happens in the difference of these two figures, right? You adding in that term seems to be very important if you're truly operating in this over parameterization regime. But yeah, it's a little bit tricky. I'm also still trying to understand this better, so I don't have like a final answer. Thanks. Okay, sorry.
So if I remember correctly, at the beginning of the talk, you said that most people approach this from like a worst case.
Yeah,
analysis,
for
but
optimization, yeah.
you approach it from like an average case. So I was wondering what you lose by approaching it from an average case, because it
Yeah.
seems to me like people would have approached it that way if there wasn't like something to lose. So I'm wondering like what you give up in the process.
Yeah, well, I'm going to circle back to Jeff's comment about non-uniform sum, or generally, if you're working with a fixed scanner or something pattern, is not this average versions, right? Because for example, we are considering Bernoulli samples for completion problem. So you kind of have like a uniform coverage over all the entries, right? But in a lot of practice problems, the sampling pattern can be very uneven. Like for example, in a recommendation problem, some user may not give you rating at all, very limited rating, but some may give you more, right? So it's going to be highly non-uniform, and that will not be covered by this theory.
Okay,
Yeah.
thank you.
You mentioned the self-super learning for the.
Oh, yes.
For the,
Fancy stuff.
not that usually for classification.
Yeah, I think it may be a overkill to use the name, but the idea is really you don't have ground truths, right? Because we don't have ground truths for this real data, so you have to just use this data, like this test data instance, it's on its own to tune the hyperparameter. So that's what we mean by self-supervised learning. It may be different from some other contexts, but yeah. Generally, this is just trying to tune the hyperparameter without access to ground truth. It's just working with the sample itself and try to figure out what is the right parameters.
I see.
It's yeah, very empirical. Yeah.
Any other questions? If not, let's thank the speaker again.
All right, thank you so much. Thank you.